Welcome back everyone to the Hello World Guide. This is another episode of our Asteroids game in C++ series, and in this video we are gonna continue by creating a system for actually detecting the collision in our game. So we are finally getting into the most important part of our game, which is the collision detection and resolution stuff. So we'll start with the simplest of all, which is the collision between our bullet and our asteroid. Now if you look at it, then our bullet is just a single point. It is represented as a single point and nothing else. On the other hand, our asteroid here is a polygon, which means it consists of a bunch of sides. Now it's not just any polygon, instead it is a concave polygon, which means that it's not convex. However, convex means that well, you can look up the mathematical definition. So yeah, if for example a triangle, it's a convex shape, and some algorithms are meant for use with only convex polygons, but our asteroid is a concave polygon, so we'll need a method to make it work with concave polygons as well. Or if we cannot find an algorithm that works with concave polygons, we'll have to split up our concave polygon into multiple convex polygons and then intersect with each of those. Luckily for us, there is an easy algorithm that works both for concave and convex polygons, and we can use that here, and it basically allows us to intersect a point and find out whether it is inside a polygon or not. Now the most important thing is that we actually need to access our polygon of the asteroid inside of bullet.cpp. For this reason, ensure that we are going to create a function called getVertexArray, which is essentially the representation of our asteroid polygon, and we're going to call it vertex array, and we are going to return it here in in the cpp file. We are just going to return the actual array member variable that we have got. Now inside of bullet.cpp, we are going to, since our game is really simple and is going to contain a small number of entities, we are going to just loop over all of those entities and collide against each, check if for collision against each asteroid present in the scene for bullet here. Now in order to do that, I'm going to go down here and create a for loop which will loop over the game entity size. So we'll loop over each of the entities, and if the type ID, and this is an operator like built-in operator in C++ to help us find out what the actual underlying type of whatever pointer or something we have got, and we are going to dereference the game entities I here, the actual entity that we are checking. We are going to dereference it and check if its type ID is equal to the type ID of asteroid, and we are going to include the header, and that means that essentially our entity is an asteroid. If that is the case, then we are going to create an asteroid pointer called asteroid, which we are going to set to dynamic cast our to asteroid pointer with the game entities we'll basically take our game entities I and dynamically cast that to an asteroid pointer. Now after that, we are going to create a const reference to a vertex array. To save performance, we are going to use const references here called polygon, which we are going to set to asteroid get vertex array, and that gives us our polygon here, and we need to check for collision against it. Now for this, we'll create a number of variables. First one is going to be n, which is going to represent the number of vertices, which we are actually going to set to one less than the actual amount of vertices. The reason is that the last vertex just connects it back to the first vertex, and that's for making sure that it looks visually correct. You can add that vertex to the calculation as well, but that's not really necessary, so we'll leave that out to save on performance. So we'll just subtract 1 from the actual vertex count here, so we don't count the last vertex. Afterwards, we are going to create an intersection count, which we will set to 0 by default, and the algorithm we are using is called the raycasting algorithm, and it basically does a lot of intersections between the point and the polygon, and if the number of intersections is even, that means that the point has gone inside and then come outside again, which means if it's even, then the point is outside of the polygon, and if it's odd, then the point is actually colliding with and inside of the polygon. So it's a very simple and easy to implement algorithm. We'll create an intersection count, and we'll also create a vector 2f called ray, and which we'll set to a vector 2f, and this needs to represent the actual endpoint of our ray, which needs to be pointing in the y direction for the actual in the right direction. So For the y coordinate we'll just pass in the actual position dot y, so of the bullet. But for the x coordinate we'll need to basically put as high of a value as we can. So for that we'll use std numeric limits float and say colon max, so we'll get the maximum float value, and then we'll just pass in position dot y as the y value. This position of course is the position of the bullet. Now that gives us the initialization, and we can start the actual processing now. For this we are going to run a for loop which goes as many times as n, so goes from 0 to n, and we are going to create a vertex 2f called p1, which we will set to polygon I dot position. So we'll set our first point will be the first position of the the first actual polygon's point, and the second point is going to be the next point, which will allow us to kind of have lines basically, so that it will represent a line, and we'll have the second vector p2 as polygon I plus 1 dot position as well. Now the problem is that we are gonna want to wrap this to the start. If it goes over, for that we'll just take the remainder of n. Do note that this is what you do in a more general form of the algorithm. However, that's not necessarily required for our case, because in our case there is always a last polygon which is always going to be going to be equal to the first point. So you can leave this out, but first let's implement it in the standard way, and then we'll do any optimizations that we have to. After we have got these 2 points, we'll check for 2 things basically here. First, this is now basically how the algorithm works. We'll check if the p1's y position is less than the position of the bullet position's y, or and we'll also check if the second y position is greater than or equal to the position of the actual bullet, and we'll if that's not the case, we'll check if p2 dot y is less than position dot y, and p1 is greater than position dot y. Now that is essentially the check on the y-axis, and only if the check on the y-axis succeed will we perform the test on the x-axis, and this will save on performance. If the y-axis test fails, we won't perform the test on the x-axis. Now for the x-axis test, we'll create a float called t, which will set to position dot y minus our point 1 dot y, and we'll divide that by position point 2 dot y minus point 1 dot y, and this is used to calculate the actual slope of the polygon's line. And for the actual intersection of x, we'll basically take our position 1 dot x, add that to we'll add t to that, and then we'll multiply that by player 2 dot not player 2 point 2 dot x minus point 1 dot x, and this will give us the x intersection. And for checking, pretty simple. We'll check if our intersect x is less than or equal to position dot x, and it's less than or equal to ray end dot x as well. If that's the case, that means our point is intersecting with the line. The actual ray that we have cast is intersecting. That means we'll increment our intersection count by 1. Remember, if this intersection count is at the end of this loop even, that means that we are inside of the polygon. So in the end we'll check if it's even, and if that's the case, if it's actually odd. If it's even, we are outside. If it's odd, we are inside. And for that we can just take the remainder of 2 and check it equal to 1. That will give us whether it's odd or not. So if it's odd, we'll just set the lifetime of this bullet to 0. Now that might seem like pretty much what we need for the algorithm. However, there is still one problem, which is that our bullet's position is in world space, where these polygons are represented in local space. So we need a way to translate these, transform these polygons from these points from local space to actual world space. Now luckily for us, the SF transform class provides a handy function to do just that. We'll create an SF transform called transform, which will set to SF transform, will initialize it to a default transform, then we'll translate it, and we'll translate it according to our asteroid's position, and then we'll rotate it according to our asteroid's angle. Afterwards, when we are setting our p1 and p2, we are going to essentially translate these points. We'll just say transform dot transform point, and we are going to pass it these, and it's going to basically apply the transformation to this point and return that point, which will set to p1. Now that should essentially allow us to get the correct transform to point in world space. Let's run that, and what you should see is that my asteroid appears, and I can go up here and I can shoot into it, and you can see that my bullets upon colliding with the asteroids automatically disappear, and that means that our collision system is working correctly, and it is working with concave shapes. You can see our asteroid is a concave shape, it's working as well. And yeah, that's all pretty awesome. When I hit the asteroid, it automatically kind of vanishes. So yeah, that means that we have got a pretty awesome system implemented for our asteroids here, and their collision with bullets. And in the next video we'll move on to more advanced collision stuff inside of our game, so stay tuned for that. I'll see you in the next one. Make sure to like and subscribe as well, and share this video with other people, and bye.